Hi students, welcome to the second part of ultrasonic testing. In this particular session, we are going to see the various techniques and methods involved in performing this ultrasonic testing. This ultrasonic testing can be effectively done by means of two methods. One is known as transmission method and pulse echo method. Now we are going to see one by one these two methods. Now coming to transmission method, the defects present in the test specimen is identified based on the quantifying the received sound waves. As we have seen in the part 1, the basics of ultrasonic testing, we said that sound waves are made to propagate through the workpiece or the test specimen, and based on the signal received back, the presence of flaws or defects are interpreted. So in this transmission method, the defects are identified by quantifying the received sound waves. Now in this particular method, we have two transducers placed on opposite sides. One transducer is used to transmit the sound waves coming from the pulsar, and the other transducer is used to receive the signals coming back from the material. Presence of any discontinuities or defects obstructs the sound waves, resulting in partial or total loss of the sound waves. The decrease in the received signal amplitude indicates the presence of defects in the test specimen. Now this is in this slide you are seeing two descriptions, where the first one shows the transmission of sound waves where the material is having no defects, and the B represents the transmission of waves where the specimen is having defect. At the top you are seeing a pulse generator, and this rectangle shows the material. On the top of the material you are having one transducer. The first transducer, it helps in transmitting the sound waves generated by the pulse generator. At the bottom you are seeing another transducer fixed onto the bottom surface of the material. It receives the signals from the material and it passes the received signal to the display unit. Now assume that, as stated in first case, the material is having zero defect or it doesn't have any flaws. So when the sound waves propagates through the material, the receiver transducer receives the signal at the bottom and it transfers the signal to the display unit. Since there is no defect, a uniform pulse signal is created in the CRO. When the image formed on the CRO is a symmetrical one, then it represents that there is no flaws. But as when we come for the second B type, you can see that there is a small defect in the material. So where the material defect is there, the signal interrupts or breaks because of that defect, and it creates an additional signal which is picked up by this receiver transducer immediately, and that signal that is retrieved immediately by the transducer is sent to the display unit. Now when you look at this display unit, apart from regular signals, you are having some peaks, smaller peaks in between. So those smaller in between peaks represents the presence of defects. So instantly the observer can look at the flaws or defects present in the test specimen. When you come for pulse echo method, the second type, the major difference when compared to transmission method is that this pulse echo method uses only one transducer. A single transducer acts as transmitter and receiver. So I will go to the representation slide. Now you are seeing the slide here. A represents without defect and B represents with defect. The output will be similar, the functioning will be similar. The only difference is in pulse echo method only one transducer is used. The single transducer acts as transmitter and receiver. Now you can see the test specimen is at the bottom, and here you are seeing a pulse generator. This pulse generator is connected to this display unit CRO, where you are having a systematic presence of the images scanned through. Now this pulse generator generates the high frequency pulse and transmits, and it passes through the workpiece and travels through the entire workpiece, and it is amplified and it is sent to the CRO. So during this process, if there is no defect in the material, then as you are seeing in the display, a uniform pattern of pulse signal is framed. Now when you come for the B type, assume that if there is a small flaw, then the presence of this small flaw inside the test specimen will create hindrance in the travel of the sound waves. And during the travel hindrance of the sound waves, the signal is instantly captured by the transducer that is present here at the top of the workpiece, and it is amplified and it is sent to the CRO. So apart from the regular signal, you will be having in between spikes or peaks. The additional presence of spikes, irregular spikes or peaks, defines the presence of defects in the materials. So the working principle behind both transmission and pulse echo method are similar. The only difference is in transmission method we are having separate transducer for transmitting and receiving, whereas in pulse echo method we are having a single transducer which is performing dual action, both transmitting and receiving. And this is accomplished by placing a single transducer at the top of the workpiece. Now coming for the type of testing techniques. Types of testing techniques, we are having 6 types. Contact testing techniques, immersion testing technique, dual crystal testing technique, straight beam testing technique, angle beam testing technique, and resonance testing technique. Out of these 6 types, we are going to see in extensive fashion straight beam and angle beam, because these 2 types are covered in your syllabus. Therefore we are going to see specifically these 2 types, but you should be knowing the names of the types. In straight beam testing technique, it usually uses normal beam to inspect material, and the transducer is in direct contact with the specimen. The determination of the discontinuity or defect is done by accurately measuring the time required for the ultrasonic pulse generated by a transducer. The time taken is accounted for calibrating the presence of defect. So the time taken to travel through a thickness of material reflects back from the surface of discontinuity and return back to the transducer. All these times are taken together, and usually the time travel for all this process, passing through the workpiece, encountering with any defect if it is present, then returning back to the transducer. All this process involves only few microseconds or even less. The time measured is divided into two to account for the down and back travel path. Down represents means the propagation of sound wave towards the workpiece or material, and back travel represents the returning back of sound waves from the material to the transducer. Down represents transmission of the sound waves from transducer to the work material or test specimen, and back travel represents the return of sound waves from the material to the transducer, and this time taken is multiplied by the velocity of sound in the test material. So it is simply represented by the formula d is equal to v into t by 2. V represents velocity, d is the distance from the surface to discontinuity, and t is the round trip transient time. The total time taken by the sound wave to pass through the material, encounter with the defect, and then returning back to the transducer. This is the round trip time. So d is equal to v into t by 2. So this is the representation of straight beam testing technique. You can see there is a pulse generator here, transducer, and this is your workpiece. The sound waves passes through the transducer and is propagates to the material and return back to the transducer and sent back to CRO unit. And during this process, if there is no defect, a regular pattern of peaks are formed at the CRO unit. So if there is any discontinuity, then additional spikes can be formed or peaks is formed at the CRO, because the transducer, it picks up the signal, and this round trip is nothing but passing of signal from transducer to the work material, then returning back to transducer to the end process. So whenever there is a peak or whenever there is a spike in the CRO, then it directly interprets that there is some sort of loss or defects present in the material. In the case of angle beam testing techniques, we are using refracted beams. In the case of the previous one, straight beam, we are using normal beam, the normal sound wave that is generated. But in the case of angle beam, we are using refracted beam. To have this refracted beam, we are using angle beam transducer and wedges to initiate or introduce this refracted shear beam or VX. An angled sound path allows the sound beam to come in from the side of the material. Usually, in previous case, the sound wave travels from the top to the bottom. It scans the material from top to bottom. The sound wave travels from top to bottom. If there is any hindrance, it comes back and interprets. But in the case of angle beam, the sound waves are propagated at an angle. So you can easily see when you look at the diagrammatical representation. So you can see here the sound waves are projected at an angle by means of a wedge. So this inclined propagation of sound wave or the refracted sound wave is performed to improve the detectability of defects and flaws. There may be improvement in identifying the defects and flaws that may be ignored when you go for straight beam type. If a reflection occurs before the sound waves reach the back wall, then it is called as first leg reflection. That means you are projecting the sound wave through your test specimen, and the wave passes through the test specimen. It should reach the end of the material or test specimen. It should reach the end of the material. But in case if there is any defect, the sound wave will not reach the end of the material. Rather, it will return back from where the flaw is. So, if the sound waves propagating through returns back before reaching the back wall or the end of the material, then it is called as first leg reflection. So, kindly please note it down. First leg reflection occurs when the sound wave, before reaching the end of the specimen, if it returns back because of any flaws or defects, then it is called as first leg reflection. This angular distance is calculated using the expression Vt into T by 2. In previous case, what we have said, V into T by 2. Here we are using Vt into T by 2, where Vt is the shear sound velocity. Why we are saying Vt? Because we are not using normal beam, we are using refracted beam. We are allowing the sound wave to pass through the test specimen at an inclined angle. Now, if the reflection comes from the back wall, if you pass the sound wave, there is no hindrance or there is no defect or flaw, so obviously the sound wave will reach the end of the specimen and it will return back. If it is such case, then it is called as second leg reflection. So I again repeat, you are passing the sound wave through the test specimen, and because of presence of some sort of defect, the sound wave doesn't reach the end of the specimen and it returns back from where the defect is, then it is called as first leg reflection. If the sound waves reaches the end of the specimen and returns back, then it is called as second leg reflection. So by knowing the angle of refraction for the transducer and the surface distance to the reflector and its depth can be calculated by the relation surface distance is equal to sound path into sine theta t, where theta r, where theta is the angle of reflection, the angle at which, the wedge at which you are keeping in to make the sound waves to pass through the material. What is that angle that you have to take into account? Now, when you come for instruments used in ultrasonic testing, the first, second, 4 and 5, you are very well versed with that, because in previous slide we have encountered with all those terms. Pulsar or receiver, it is used for generating high voltage pulse. When you go for transducer, it transmits the sound waves and it receives the sound waves. Oscilloscope or digital signal screen, it is the screen or it is the device on which the end user will be looking at the interpretation. Receiver or amplifier, which is used for amplifying the received signal. So all these parameters are very well known to us. The new term what we are encountering here is couplant. Now, couplant is a medium that is applied between the transducer and the test specimen. For example, normally when we go for scan center, when you want to take a scan of your abdomen or pelvis, what usually done is the doctors, they usually place uh, a liquid type or a gel type content over our chest or pelvis, that gel is applied onto the body so that there should be no air gap between the probe through which the waves are passed on and the body. To eliminate that air gap between the body and the probe, a gel is used. Similarly, a couplant is used to reduce the air gap between the transducer and the surface of the part to be inspected. So, couplant is used to reduce the air gap. Now, coming for mode of display, you are getting the interpreter, you are getting the signal onto your display. Now, how you are going to interpret those things? So, communicating the flaw size and shape is a very crucial part of this testing process. The signals are transferred into the CRT screen to obtain the image of the defects. The presentation of the image of the defects on the CRT screens are done as A scan, B scan and C scan. The A scan is one of the simplest method of display. The time of flight of the pulse is represented on x-axis. Amplitude and the echoes are represented in y-axis. The A scan shows the size and position of the defect under the probe. The probe is used or moved in a systematic manner. So when you move the probe, it sends ultrasonic energy into the material. So this is your A scan. The material is here under inspection and you are having a probe here, and this probe is moved. The probe is moved in a systematic pattern over the test specimen. So as you move systematic manner, the sound wave passes through and the information is recorded in the display. In this A scan, certain amount of ultrasonic energy is reflected at the top and bottom faces of the material. The echoes from the top and bottom faces gives the initial and back wall peaks on the CRT. Presence of any defect will be indicated. Presence of any defect will be indicated as small echoes in CRT. This small echoes is nothing but in CRT you will be having a peaks. So the size of the defect is directly proportional to the size of the peaks formed on the CRT. So smaller is the peak, then smaller is the defect. Higher is the peak, and then higher is the defect. In B scan, two-dimensional image is performed on a stationary specimen. The dimension of the specimen is displayed on the x-axis and the travel of ultrasonic pulse is displayed on y-axis. The probe is moved to or is made to move along a line on the top of the material, and the sound wave will transfer through the material performing its own process, and the interpretation will be highlighted in the CRT. So when you go for this B scan, you can see the workpiece is here, probe is here, and the probe is moved in this direction, scan direction, and as the probe is moved towards the scan direction, the sound wave travels through the material and it's accordingly the peaks are formed in the CRT. So the benefit of B scan is that this scan, B scan, presents cross-sectional view of the material along a line, and the defects or the echoes are displayed as a bright spot. So when you move, as the scanning process is going on, the cross-sectional view of the material along a line, it provides depth of flaw from the surface of the material and the length of flaw along the line of movement of the probe. and moreover the brightness of the echo is proportional to the echo amplitude. In ski scan, it is considered to be the best method to display the flaw depth. As usual, the probe is moved onto the surface of the specimen, and the echo of the scan output produces a shaded line with varying intensity, indicating the absence of flaw. Whenever there is no flaw, it is represented as a shaded line. If there is absence of shaded line, then it indicates that there is a flaw in the shape. In this method, the probe is continuously swept line by line on the top surface, and usually this method is employed in pipes and pressure vessels and also in composite material for determining its intensity. Now you look at this method. The material is here, the material to be scanned is here. You are having the probe and you are moving the probe continuously on the surface. If there is no flaw, then you will be having continuous line. If there is any flaw, as you see in the defect as a circular defect, so when there is a circular defect, there will be absence of consistent line, continuous line. The continuous line will be broken. So whenever there is a broken line, then you can easily identify that there is a flaw here. So it is mostly widely used method. When you come for advantages of ultrasonic testing, this type of testing is sensitive to both surface and subsurface discontinuities. Depth of penetration for flaw detection is superior. Even small flaws can be detected. Large specimen can be inspected in very short duration. It is very cheap and high speed of operation. Minimal part preparation. It is highly sensitive and therefore provides greater accuracy, non-hazardous and instant result. When you come for limitations, the surface which you want to test should be accessible and smooth. Complex geometry we cannot do, because if the complex geometry is there, then you cannot move the probe much easier. There will be not a consistent or continuous contact between the material and the surface. Therefore, complex geometry cannot be done. It is difficult to inspect. Reference standards are required for both equipment calibration and characterization of flaws. Not suitable for coarse grained surface. Linear defect oriented parallel to sound beam may go unnoticed. Requires coupling medium. Skilled operator required, and interpretation can be difficult. So in case when you are going for coarse surface, in coarse surface there will be some voids. So when you go for testing, the presence of small coarse material, small voids may result in interrupted interpretations. So these interrupted interpretation may result in wrong decisions by the end user. So therefore, highly skilled person required for interpreting the results. So when you come for applications, testing ferrous and non-ferrous pipes, rods, bars, detecting corrosion in petroleum and gas supply lines, erosion and corrosion thickness gauging, testing welds, fatigue detection, inspecting large casting and forging products or parts, estimation of void content in composites and plastics, and inspecting structural integrity of aircraft parts. So these are the wide application of ultrasonic testing. So I believe that this session would have been very useful for you, and you might have learned some of the advanced feature of this ultrasonic testing, and I kindly request you to go through the assessment sheet attached in the descriptive session to evaluate yourself how far you have understood the content delivered in this session. Thank you and God bless you all.